This question came in GATE 2020 for 2 marks. In this question, in a digital communication system, a symbol S randomly chosen from the set S1, S2, S3, S4 is transmitted. It is given that S1 equals to -3, S2 equals to -1, S3 equals to +1 and S4 equals to +2. The received symbol Y equals to S plus W, where W is a zero mean unit variance Gaussian random variable and is independent of S. Pi is the conditional probability of symbol error for the maximum likelihood decoding when transmitted symbol is Si, and we have been asked to find the index I for which the conditional error probability Pi is the highest. More detailed explanation on maximum likelihood decoding and conditional symbol error probability is discussed in the NPTEL lecture Principles of Digital Communication, lecture 30 by Dr. Abhishek Dixit of IIT Delhi. Now we will look at some of the concepts involved in solving this problem. The first concept is transformation of random variables. So if x is the input and z is the output, x is transformed into z by adding y, that is z equals to x plus y. Now if x and y are independent, then the PDF of z can be found out from the PDF of x by shifting x by y, provided y is a DC value like +3, -1, +2, like that. But conventionally, PDF of z is the convolution of PDF of x and y and is given as. And the next concept is maximum likelihood decoding. For maximum likelihood decoding, the decision boundary between two adjacent signal points will be the arithmetic mean, since the probability of transmission of the symbols are equally likely. So if you have two symbols, one at -3 and the other at +1, then the decision boundary will pass through its arithmetic mean, which is -1. So any point which lies on this side will be decoded as -3, and any point which lies on this region will be decoded as +1 according to ML decoding criteria. Proceeding with the solution, we have been given that S and W are two independent random variables. Hence the random variable Y can be directly found from W by shifting W by S, since S is a DC value. So we have four corresponding cases, S1, S2, S3, S4, and they are as follows. And W has been given as a normal random variable with zero mean unit variance. Now we will look at how the received symbols look like. So this is how the received symbols look like. All of them are identical Gaussian with unit variance but shifted means. S1 is centered at -3, S2 is centered at -1, S3 at +1 and S4 at +2. In order to draw the ML decision boundary between S1 and S2, we have to find the arithmetic mean, which is -2 for S1 and S2. Hence this line drawn is the ML decision boundary. Anything on the left side will be decoded as S1 and anything on the right side will be decoded as S2. So the probability of a symbol being correctly decoded as S1 PC is this region. So we know that PE, the probability of error, is 1 minus PC. Hence, as PC increases, PE decreases. The probability of symbol being correctly decoded as S2. Now for S2, it has two decision boundaries, one with S1 and other with S3. S3 is centered at 1. Hence, we have another ML decision boundary at 0, which is the arithmetic mean of -1 and +1. Hence, for S2 being correctly decoded, this is the corresponding probability region. So, as we said that as PC increases, PE decreases, we see that the area under this curve is less than the area what that was in this curve. Hence, we can say the probability of correctly decoding for S2 is less than that of S1, or we can say that the probability of error for S2 is greater than the probability of error for S1. Now for S3, which is also bounded by two decision boundaries, one for S4 and the other for S2. S2 it is already 0, and for S4 the arithmetic mean comes out to be 1.5, and hence this is another ML decision boundary. Now this is the region where this symbol is correctly detected as S3. So as we can see that this region is even smaller than the previous region, and hence the probability of error for S3 is greater than S2 as well as S1. So we can write PE S3 is greater than PE S2 is greater than PE S1. Also, we can say that the probability of error for S4 is lesser than S3 because the probability of being correct for S4 is this region. So the PC is larger for S4, as a result the PE value is lesser for S4. Hence we can also say that PE of S3 is greater than PE of S2. So from these two we can say that symbol S3 has the highest probability of error. This is quite intuitive because this distance is lesser than this distance. This is 1.5, this is 2, this is again larger, this is also large. So we can say that S3 is the one which is having the largest probability of error. Now we will look at another shortcut technique which is based on intuition, the nearest neighbor distance. For S1, which is at -3, it has one neighbor only, S2. Hence, the nearest neighbor distance is 2 because it is at -1, -3 and the S2 is at -1. For S2, it has two neighbors, S1 and S3. So, the distances are 2 for S1 and also 2 for S3. For S3, it also has two neighbors, S2 and S4. For S2, the distance is 2, but for S4, the distance is 1. For S4, it has only one nearest neighbor, which is S3, which has a distance 1. So the shortest distance is for S3. The shorter the nearest neighbor distance, the larger the probability of error. But for S4 and S3, this other distance is infinity because there are no other symbols which are on this side of S4 and no symbol on this side of S1. Hence we can assume it to be infinity. So clearly S3 has the shortest nearest neighbor distance and has the highest PE value. So the value of I is 3, hence the correct answer is 3.